Dominic.
Hi, I actually have a question for two questions, one for each speaker. So for Jeongwan, I wanted to ask why you call this condition homogeneous? Because, like, for example, suppose I take a stack of 2D topological orders and I stack them in three dimensions, but each layer is a different topological order. Like, this seems like a very inhomogeneous state, but still somehow it satisfies your condition.
Yes.
So why do you call it homogeneous?
So my main viewpoint, well, I don't have a strong reason to justify my terminology, but the overall picture I had was the following: the ball you should avoid to satisfy my condition can be anywhere, and can be any size. In particular, if you have a torus, for example, then your ball could be as large as the full torus minus very thin two strips. And they can be placed anywhere. So the two strip, the operators that you have avoided the region I gave you should be supported on the thin strip, for example, on the top right. And at the same time, you should be able to deform it to the lower left corner. So they are somehow connected conceptually. And that picture is basically the only reason I call it spatial homogeneity. Nothing much deeper beyond that.
But it is satisfied in this example I mentioned. Though, is it where you have a stack of different topological orders?
Let's see. I think so, because the ball in the ball you throw in three space will decompose into disjoint disks in each layers. In each layer you can avoid them.
Okay.
Yeah.
Okay, thanks. And so for the second speaker, I wanted to ask, these mobility constraints, they result from projecting into the lowest lambda level. So if you include lambda level mixing, do the quasi-particles able to move now?
I think with lambda level mixing, then I think that you can move with the mass not equal to 0. You can like move.
I see. Thank you.
If I can comment on this, sorry for interrupting. There are no mobility constraints in the lowest lambda level. The sort of constraint that emerges from the projection is that the dipole moves perpendicular to its dipole moment, kind of automatically. But there are no lines predetermined along which you can move. So you create dipole that has some orientation in space. And the moment you create
what about the fractonic particles that were mentioned?
There are no fractonic particles there.
Oh, I thought.
So the constraint that you get is that motion is always perpendicular to dipole moment, but the dipole itself can be oriented any way you want. And there are no single particles that cannot move. Like dipole is as far as you can resolve.
I see. Well, I think that's the same situation as in some of these, fracton higher rank gauge theories that people have discussed, right?
It's similar, but okay, I'm not going to try to spend more time trying to point out the difference, but there is subtle difference. The momentum in those gauge theories is like a separate conserved charge, right? And dipole is also separate conserved charge. The translation variant and the conserved dipole. Whereas here, the reason dipole is conserved is because it's equal and perpendicular to momentum. Yeah. So you see, there's subtle difference how charges are arranged. In the first case, momentum and dipole, two different things, different symmetries. In this case, it's the same symmetry. Dipole conservation is part of the space-time algebra of symmetries. So that's the interesting difference. I cannot, and because of this, dipole can be oriented any way you want, but then it moves on the perpendicular to its dipole moment. And there is no particle that it's made of. Just in the lowest lambda level, everything is non-commutative. You cannot resolve any particle bigger than magnetic length, scale bigger than magnetic length. So if you create an excitation, it already is fuzzy on the scale of magnetic length. And if it moves, then it distorts. And it has like ellipsoidal shape. So ellipsoidal shape gets dipole moment. So that's the picture that you should have in mind. It all looks very similar to fractons, but there is some subtle differences. Okay, sorry for interrupting.
Yeah, so basically, the same as Andre address. The dipole moment conservation, you see that when I derive this from the global symmetry, you see that the conservation of dipole moment come from the magnetic translation, and it's nothing but it's conservation of momentum. However, in the lowest standard level limit, you can rewrite the momentum in terms of like the dipole. So basically, the conservation of dipole and the conservation of momentum are the same thing.
Thanks.
Okay, next is by Meng.
Hey, so I have a question for Jeongwan. So you use this recoverability of the ground state, the perpetual ground state, to argue that fractal models also satisfy the condition.
Mm-hmm.
So I'm just wondering, like, in what sense the definition of your homogeneous topological order is stronger than just saying any patch of my ground state is recoverable, like in the error correcting sense? Is it strictly stronger? Like,
it's a slightly stronger. Well, it's a subtle thing. In the commuting projector Hamiltonian, there's no distinction. The difference is that when you require the correctability for one patch, it does not necessarily immediately imply the correctability of disjoint sets. But yeah, again, the correlation is strictly zero case, correlation length is strictly zero case, that they're all the same. But in the approximate case, there's uncontrollable vector that creeps in. So then the my notion becomes a little stronger.
if I instead say, let's demand correctability for joint patches, does that become equivalent to the definition?
If you require correctability for all patches, for all, for disjoint ball of patches,
right?
I'm sorry, yeah, disjoint union of balls, yeah, then they become equivalent. Yes.
I see. Okay, all right, thank you.
Okay, next question by Media Technology Services.
Yeah, that's me. I have a question for the first speaker about the bound. In the case d equals 2, the exponent is 0.
Yes.
So the bound is a constant. Can there be a correction to that?
Correction?
So I wonder whether for d equals 2, the fact that the bound is L to the 0, whether there is a bound which is log L.
No. Well, with my very definition, there would not be any correction. Even the constant is fixed by the genus. So in particular, in the genus 0 sphere case, the degeneracy bound becomes just 1, strictly. You could allow for corrections by softening, the criteria, but it's not immediately what softening would be most natural thing to choose.
I have a variant of this question, even in higher dimensions. So we are in d equals 3 and something proportional to L.
Yes.
When you say an inequality L, can there be an additive correction which is subleading than L?
Oh.
Do you really mean is that the answer is that the left-hand side divided by L and the limited L goes to infinity is less than a constant? Or can it be that the answer would be, say, L plus log L, but with a plus sign?
No, my argument would not see that additive corrections. Your first assessment is correct. The left-hand side divided by the L in D equals 3 case will be bounded by a constant. That's what I'm claiming.
But only in the limit,
Sorry?
only for large L.
Yes, yes.
Okay. Thank you.
Are there any other questions? Meng, do you have another question?
Yeah, so maybe I have a follow-up question about Dung and also Andre's comment. So in what sense I cannot resolve a single, say, laughing quasi-particle? I mean, does it make sense to ask the mobility of a single laughing particle in the lowest Landau level?
So I believe that in the lowest Landau level limit, then I think that quasi-particle has a restricted mobility from the symmetry, is what I believe.
But yeah, I mean, it's true in the sense that, you know, it's a charged particle in a magnetic field, so it's localized. But I mean, is it possible to introduce, for example, perturbations that break translation variance strictly within lowest Landau level and make it mobile?
I think no, I don't think that you can do that from the formalism that we have.
Okay, like you cannot add a term.
Yeah, I think that you need to do the Landau level mixing to restrict this constraint.
I see.
And maybe I can add that, you know, we usually do write the trial state that has precise position of a quasi-particle, but that's really a toy model, right? If you really think about lowest Landau level physics, the constraint says that you cannot resolve anything smaller than the magnetic length. So quasi-particle is also, it doesn't have precise position. You just can localize it only up to the scale of magnetic length. As it moves, this area where it's localized, it still has the same area, but it distorts its shape. It goes from circular to elliptical, and that's and this elliptical shape gets a dipole moment.
Okay. It still has charge, right?
It's perpendicular to the direction of motion.
You mean the dipole moment is perpendicular?
Yes.
Yeah.
So if we start from let's say like localized laughing particle that has a charge, it still has a charge, right? That's...
Sure.
So
yeah, there you have to well, the laughing quasi-particle is maybe a bit unpleasant example to think of because it has charge. Maybe a little better is to think about composite fermion, which is a combination of flux and charge, and on average is neutral. That thing has well-defined dipole moment, no matter where you put the origin. If you try to move this, the dipole moment will always be perpendicular to the momentum.
Yeah, I see. Okay. All right. Thank you.
And how to say the movement of the composite fermion also can be derived using the Galilean invariant, and in this way you can see that explicitly from the beginning the momentum of the composite fermion will be perpendicular to the dipole moment. So you can look up my paper with Sun and other collaborators to see this appear from the beginning. So in the talk, I discussed the electron theory version, but in the composite fermion theory version, you see that it appear from the beginning by the Galilean invariant.
Question from Nat.
Yeah, I have a question for Jeongwan. So I was wondering about the relation, the problem you posed about the defect network model. in what sense do you think there would be a problem in like, is there something about the defect network that you think would violate your constraint, or?
No, it's just that the defect network construction is so general that at some point there will be a lot of absurd instances, I think, and I would like to. I was proposing that condition to rule out those absurd instances. Yeah, I hope it gives some guidance.
So what would be like this absurd instance in the defect network? For example, like infinitely many rotational.
Right. Yeah, very absurd scenarios like you can connect many conventional topological order blocks at a distance scale that is much smaller than the overall diameter, but still larger than your lattice spacing. And that intermediate length scale can be anything. And you would like some criteria to choose that length scale. And the length scale should be, really microscopic in my sense. Well, in order for that construction to satisfy my condition, otherwise it would not. It will be violated.
But doesn't by choosing this length scale, doesn't that like increase the density also, or?
Oh, no. Well, concretely, you can join like a Z2 3+1 D gauge theory blocks in a fashion that there's at the boundary there are like 3 or more blocks are joining along one surface, and you can have a network of those, and each block size can be like, say, square root of the total diameter. In that scenario, the two length scales, the full diameter and the block size are both macroscopic, but there is still a hierarchy left. And if you apply my criterion there, then since each block is somewhat fixed, and if the block size is considered as O1 in your convention, then it looks like a Ising model at that point. And at that point, you are violating my criterion using balls of size square root L. And I want to avoid that situations.
Mm-hmm.
Jeongwan, if I only consider defect network where these blocks, whatever that means, are the size of these blocks are taken to be constant, compared to like a truly microscopic short distance cutoff, then as I'm taking thermodynamic limit, if I always keep myself in that kind of limit, there's no absurd construction. Is that true or not?
I think you need to be more quantitative. Just saying thermodynamic limit in this case is not sufficient. Both square root L and L are diverging function of L.
Right. So I think what I mean that let's say I keep a little L a constant, and it doesn't.
Oh, right. In that case, now, well, that's a one necessary condition, but probably not sufficient. You need to tune a lot of intermediate parameters that enters in your construction to satisfy my condition.
Okay.
And perhaps that aspect is more interesting. The topological defect network, well, naively allows you to just juxtapose whatever conventional blocks you may have.
Yeah.
And that juxtaposition clearly not something you want to study. So there must be some criteria that I can declare, oh, I have glued them together. And my criteria may be some weak form of that basis that you can say, oh, I have glued them.
Well, I guess you want to glue them, but still somehow keep this notion of defect network. But otherwise, if I'm always staying in this limit, it's just, you can always think of each block as just a huge collection of qubits. Okay, all right. Thank you.
Are there any other questions? Okay, thanks both the speakers for really nice talks. Let's take a